at the stuff I sent out, I looked back at what I'd done at rectification last week and decided I thought I'll tidy that up a little bit this week. And I've got some circuits I can show you on the I circuit on my iPad that'll help to clarify what these waveforms look like and how rectification works. So we're going to look at half wave rectification with a single diode, the full wave rectification with the bridge, and have a look at how capacitors can be used to smooth the output a bit. And then I'm going to issue and introduce assignment 2. Okay. So rectification, as I said last week, is the process of turning an AC waveform like that on the left-hand side into a direct current waveform like that on the right-hand side that doesn't cross over the 0 axis. So really ought to have put an axis on that as well, showing that that's DC because it doesn't cross the 0 line. Yeah. So half wave rectification, as in the circuit shown, uses a single PN junction diode, and doing the red positive half cycle of the AC waveform, current will flow and we get an output, this half here. When we go into the green half cycle, the diode is reverse biased. We don't get current flow and the output is flatlined. And then in the next red half cycle, we get an output again, sorry. Blue. And so on. Yeah. So as you'll see in a minute, we get a DC level or an RMS value of that waveform, which is what you'd measure if you measured it with a meter that sits somewhere around here. The average or RMS value of that waveform. Yep. So I'm just going to share with you now my I circuit, which is this. Okay, we'll have a little bit of a better play with this. So we got a 10 Hertz AC signal, a single diode, and a resistor as a load. We turn that on and take a look at the output wave, the waveforms. You can see I'm going to make that a bit bigger. So the yellow waveform is the AC. If you look down the bottom at the values, the AC waveform is 30 volts peak. So you can see it's got a peak of 30 volts. Look at it closely. And its RMS value is 21.15. The green waveform, you can see it doesn't quite reach the same peak at the top. That's because of it's losing the approximately 0.7 volts of the half waveform to as the voltage across the diode to open the gate, and its RMS value. So out of 30 volts, we're getting 14.37 volts. So that's what we would measure if we put a digital meter on that DC output across that resistor as 14 volts. Yeah. And if you look where the green crosses 0, you can see the little step where that 0.7 volt gating voltage is, where you're losing a little bit there as well. Okay, everyone happy with that? Good. Right, let's just go back to the circuit. All right. So hopefully that's useful. You can see the current flowing in a circuit as well. It's quite a useful little program once you get used to it. All right. So that's half-wave rectification. We rectify half of the waveform. Not used that much. You won't find it used very much because it's quite wasteful in it. In the only converting less than half the energy. All right. So moving on then to what's called full wave rectification. It uses 4 PN junction diodes connected in a bridge like that shown in the middle there, and I've drawn it twice. The top one shows the red half cycle, and the current flows in the directions of the red arrows. So it flows along here, down through that diode, through the load, back up here, through this diode, because that's forward biased. Now, a lot of people say to me, why doesn't it go up through this diode? That's because the voltage here, 30 volts, is much higher than the voltage here. Is going to be about 0.7 left. So it's this diode was forward biased. This one here was reverse biased. Travels down there and back where it came from. In the bottom circuit, you'll see, let's just say that's that half cycle of the DC output. In the bottom circuit, the green half cycle, current's flowing in the opposite direction from the source up through this diode, but it's going the same way through the load as the red half cycle. Up this diode and back to there. So you get a green half cycle, fills in the gap. Yeah. And so the DC level in that system is going to be, in blue, somewhere up here. The RMS value that we measure with our meter. Okay, so that's full wave rectification. Let's see if I can show you that on my circuit. Bridge rectifier. So here's the bridge rectifier. I've got 1 hertz on here, so you can see a bit better that it's going backwards and forwards in the AC part of the circuit in the middle, and you can see the different diodes conducting. But in the load, the little yellow current arrows are always going in the same direction, so that's DC. And again, if we look at the waveform diagram, you can see that the yellow one again is the AC. It's peaking at 30 volts. The pink one is the DC. It doesn't reach the same level. We're losing 2 gating voltages, so we're losing 1.4 volts effectively here with the voltages across the 2 diodes. But we're actually filling the gap in. So where we had I think it was 14 volts RMS before, we've now got nearly 20 volts RMS from the full wave rectification. Yeah, let's just check that back. So half wave, full wave RMS is 19.94 volts. We just pop back to the half wave rectified circuit. We've got RMS 14.65. This is over 30 volts, remember. So we're putting in a peak waveform of 30 volts that has an RMS of 21.6. So the AC RMS is 21.6. So with the full wave rectification at that 21.6 volts, we get 19.4, but the half wave only 14.65. So moving on from that, what we can do is add capacitor smoothing. So if after the rectifier we put a capacitor in parallel, or capacitors if we want more storage, what that does is in the rising half cycle of the full wave DC output, the capacitor charges up, so we get charge on here, and then when it goes down again, it discharges some of that to the load. So we end up, instead of the lumpy output that we had before, we end up with this output here, where we've filled some of the gap in. The capacitor is helping to fill that gap where that waveform was like this originally. The capacitor has filled the gap a bit. Yeah. So capacitor provides current when the voltage is dropping in an attempt to fill the gap. The smooth output will always have an element of ripple. Yeah. So this is where I'll put the little arrow in there. Let's go red. This little arrow in here, that is called a ripple. It's the voltage that sits on top of what would be a flat line. Okay. Now that ripple is affected by the load that you put on the power supply circuit. This is a relatively simple, what's called unregulated power supply. The magnitude of the ripple will depend on how much smoothing capacitance there is, and secondly, how much current is drawn from the rectifier circuit. Yeah. So if we have less capacitance or we take more current, then we're going to go deeper into the gap, and we're going to end up with a lower DC level about here somewhere. If we add more capacitance, we draw less current, you get less ripple. Yeah. And I can demonstrate that now on the I circuit. So bridge rectifier with smoothing. Okay, so if we look, we've got, I'm going to just change the resistor to at the same as we had with the other two circuits. We've got a resistor of 510 ohms and 100 microfarads of capacitance. We're on 10 hertz. If we look at the pink waveform, we can see how it's filling in the gap between the peaks that we had before we used smoothing. So this pink line is not it going down all the way down to zero every half cycle. So we've got now an RMS level of 23 volts or so. It's not consistent. So with 100 microfarads, 510 ohms, we're getting 22.8 volts there or thereabouts. Okay. Now, if I increase the capacitance, watch what happens with the well, isn't that a running? Ah, here we go. To 1,000 microfarads or a millifarad. Look how much that's filled that gap in the top there. We've got a lot less ripple, and we're now 27.42 volts RMS. So if we add 1,000 microfarads, 510, we get 27.42 volts DC, the RMS value. Yep. If I take that down to 10 microfarads, we drop a long way down into troughs, and therefore our RMS goes to about 20 volts. Yeah. If I alternatively reduce the resistance so that more current flows, we drop down in, we get 19 volts. If I increase the resistance, that has the same effect as that will reduce the current, and therefore we won't discharge too much between the cycles. We got 27 volts, 27.5 volts. So as you can see, there's an effect on when you have a smooth power supply, the amount of ripple that you have on that will be dependent upon how much smoothing capacitance you have, and also on how much load, how much current you draw from that power supply. Okay. Anyone got any questions relating to that?
No.
No? Was that useful to see the circuits operating?
Yeah.
Yeah, good. Right, what I'm going to do now is share the assignment with you. I'm going to talk you through the questions in it. I can find it.
All right, have you got the answers as well?
No, I'm not going to talk you through them.
Oh, what?
Well, what are we doing here then?
That's the only reason I'm here.
Task 1 looks fun anyway.
Yeah, that's fun.
Isn't
Yeah.
it? Oh,
How many passes is it? 1, 2, 3, 4.